From physics-informed neural networks that struggle when equations become tightly coupled, to fresh stability theory explaining why SVRG can learn with stronger guarantees, and on to Muon's surprising Hamiltonian view as a spectral mirror method, this episode connects three very different advances in AI optimization. Together, they reveal a common theme. Better understanding the geometry of learning can unlock faster training, stronger robustness, and sharper theory. If you're curious how modern optimization is reshaping machine learning, this conversation is for you. Let's explore the first paper, Coupling Robust Accuracy in Multiphysics, Physics-Informed Neural Networks via Kronecker Preconditioned Optimization. This paper explains why physics-informed neural networks for coupled multiphysics systems lose accuracy as coupling strengthens, and shows how Kronecker Preconditioned Optimization fixes it. For linearly coupled PDEs, the authors prove that the standard neural tangent kernel, k equals jj, has spectral radius growing as omega gamma squared, where gamma is the coupling strength, so the stable learning rate shrinks as O1 gamma squared. In contrast, block diagonal Gauss-Newton preconditioning yields a preconditioned kernel Kp that decomposes into orthogonal projectors and satisfies lambda max Kp is less than or equal to S, with S equal to the number of networks, independent of gamma. In the over-parameterized regime, they observe equality. Lambda max Kp equals S across all tests. They connect this theory to SOAP, a Kronecker factored optimizer, and inverse gradient norm balancing, reporting that SOAP plus GN is the only method to keep coupling degradation near 1 times across 234 experiments on 1D thermoelasticity, 1D reaction diffusion, nonlinear Nernst-Planck-Poisson, and a 2D electroosmotic flow benchmark. As strongest coupling, SOAP improves final L2 error by 41 times to 143 times over atom, while SOAP plus GN achieves 1.3 times 10^3 relative L2 on a 2D. 6 PDE electric double layer resolved electroosmotic flow problem where atom plus GN fails with L2 above 0.9. The key novelty is the spectral argument. Coupling hurts because diagonal optimizers cannot see cross-network Jacobian blocks, whereas blockwise second-order structure makes training coupling robust. Let's explore the second paper, Learning Theory of the SVRG Generalization and Convergence Analysis. This paper gives the first non-vacuous learning theoretic analysis of SVRG by proving algorithmic stability bounds that exploit its two-loop variance-reduced update instead of treating it as a black box. The key technical move is to rewrite each SVRG step as an SGD-like iterate plus a zero mean correction term, then control the extra reference point gradients with new Lyapunov functions. This removes the usual Lipschitz assumption by using the self-bounding property of smooth non-negative losses. For convex alpha smooth objectives, the paper proves on-average model stability, with bounds scaling with the empirical risks along the trajectory, and combines that with a new convergence result under the looser step size condition. Eta is less than 1, 2 alpha, improving on the earlier eta is less than 1, 4 alpha requirement of Reddy et al. 2016. From this, it derives excess population risk bounds of order 1, square root n in the convex case, and 1, 1, nu in the mu strongly convex case, matching minimax lower bounds up to logarithmic factors. The same framework extends to Saga, yielding analogous stability and optimal risk guarantees with weaker step size restrictions than the original 2014 analysis. Experiments on binary logistic regression using MNIST, A9A, W6A, and mushrooms confirm that the empirical stability distance grows with step size and that the theoretical upper bounds track the observed distances closely, especially as training progresses. Let's explore the third paper, Muon, a Hamiltonian probability gradient flow perspective of Muon optimizer. This paper reframes Muon as a spectral trust region mirror method and then lifts it to a phase-space probability flow on matrix-valued parameters. The central technical move is a smooth regularization of the hard polar factor map, orth p, via orth epsilon p equals u diag sigma, square root sigma 2 plus epsilon 2 v, which is exactly the gradient of a Fenchel dual smoothing of the nuclear norm. This makes the Muon step a mirror, prox update with momentum as the dual coordinate rather than an ad hoc normalization. From that structure, the authors derive an inertial, continuous time limit for finite particle systems. Then, a McKean-Vlasov continuity equation overlaws micro T on WP pairs. The resulting dynamics are a damped Hamiltonian probability flow with Hamiltonian epsilon gamma mi equals integral psi epsilon p d mi plus gamma r integral fw d mi, and they prove an exact dissipation identity dh epsilon gamma divided by dt equals m's gamma integral p orth epsilon fd mu is less than or equal to 0, even though the target objective j rod itself need not be monotone. Under gradient dominance, bounded momentum, and curvature alignment assumptions, they obtain exponential objective gap decay. On the scalar specialization, the rate is xpane-c alpha, RT, with explicit constants. They also prove propagation of chaos with O, 1, n mean square particle error, and show that the hard muon limit epsilon 0 yields a subsequential differential inclusion with nuclear norm subgradients. The framework extends to product matrix spaces and transformer mixture of experts models by treating expert weights and router parameters jointly. In synthetic matrix mean matching and teacher-student experiments, regularized muon removes the is approximately equal to 10.3 residual floor, seen with hard polar and Newton-Schultz updates, and reaches losses as low as 2 times 1032 inches one setting and 6 times 10.7 inches another. That's a wrap on today's AI paper highlights. Thanks for watching.